Hello. I would like to talk with you today about a really cool theorem in Calculus 1, the mean value theorem. I'd like to start by drawing a picture to demonstrate it, give you an alternate name for it that I think better describes the theorem, and then practice that theorem to actually do what it says that it guarantees we can do. Okay, so I need to draw a function here. Let's take that to be our function, and we're going to focus our attention on an interval from A to B. Am I actually vertically aligned? There we go. Now I actually make it to A to B. Okay, and so this is our function f of x. That's our x-axis. Cool. Okay, so the mean value theorem says if I take the line that connects these 2 points, if I take that line, somewhere we are guaranteed that there exists a point on this curve that has tangent line parallel to this one. So this is a tangent. This line must exist. So this line right here is essentially what would happen if the function just increased according to the average, or in some sense the mean value. Okay. So that line must exist. The mean value theorem says that it has to. Let's get a little more symbolic. Let's get a more symbolic on it. So let's take if f is a differentiable function on an interval from A to B, then there must exist a C in A, B. There has to exist a point C. I didn't label C for you, but what C is it? So right here, that's C. C lives inside of the closed interval from A to B. C is in A, B. The C has to exist. Such that, what's special about this C? Well, f prime at C is equal to f of B minus f at A all over B minus A. So the slope of the tangent line right here, the slope of this tangent line right here matches the slope of this line right here. So if you want to see the f of b minus f of a, b minus a on this diagram, well, this distance along here, that distance right there is b minus a. And then this height right here is f of b minus f at a. So it's literally a rise over run argument on this line right here. And so how much change happened, how much time did it take for that to happen, gives the average rate of change over this time interval. And we're guaranteed that somewhere in that interval, the function actually took on that average rate of change. The average rate of change has to be taken on somewhere inside of a closed interval. It has to. And I think this is like so super cool. I love that this happens. Okay, so the mean value theorem says that this C exists. It doesn't tell us how to find it. That's up to us. Okay, so it's an existential must exist. It's existential. It's not what we call that's not it. Whatever. It's existential. It asserts the existence of it. but it doesn't say how to do it. It's not constructive. It doesn't say how to construct the number. I generally like constructive theorems more than I like existential theorems, but they're both good. I like both of them. Okay. So let's go ahead and do this in an example here. I'm going to wipe this diagram because I want to model this practice. So I'm going to draw a new diagram. We're going to use a specific function as we do this. And I want to use the square root function because it's easy to differentiate. We know some square roots, and so we can really focus on what the theorem is saying rather than getting lost in details on like some exotic function. Okay, so I'm going to choose to use an easy to work with function so that we don't get sidetracked by something that's more complicated. That's the only reason why I am choosing a simple function for doing this. It will work on any function which is differentiable on a closed interval. So let's take f of x equals the square root of x. And let's verify Rolle's theorem. Nope, this is not Rolle's theorem. My brain is somewhere totally weird. This is the mean value theorem. I think of it as the average rate of change theorem. Verify the MVT on the interval from 1 to 9. Where this has been specially constructed so that the numbers are easy to work with, okay? Don't expect the numbers to be easy to work with necessarily. Okay, so we should draw a diagram because I think that everything comes from the picture. In my mind, that's how I do things. Okay, so let's draw some axes. Here, let's have x, and let's draw the square root function. Let's do the square root function like that. Let's call that 1, and let's call that 9. So let's go up onto thing. The height here is the square root, so that's 1. And this is 3, because that's the square root of 9 equals 3. If I draw the line that connects these 2 points, the place that I'm going to find that the function actually takes on tangent line with that slope is going to be right there. So it looks by my mediocre hand-drawn diagram that it's going to be closer to 1 than it is to 9. Okay. So we want to construct this number over here. My interval is from 1 to 9. So 1 is A, 9 is B. So f of A is 1, f of B is 3, and so then I have f of A, nope, f of B. It doesn't matter because there's a minus sign. So you can as long as you flip both, it works out okay. So actually I started out writing f of A, but I just won't be consistent. F of B minus f of A all over B minus A is equal to 3 minus 1 over 9 minus 1. And so that's equal to 2 over 8, which is a quarter. So the slope of each of these lines is a quarter. That's the average rate of change over this interval. That's what we just found. So we want to find C such that the slope of its tangent line is a quarter. Okay. So the slope of this line equals f prime at C. So we need to compute f prime at C. I don't know what C is, but that is not going to stop me from writing it down. I'm absolutely going to still write it down. So f prime of x is equal to, let's see here, we're going to differentiate x to the 1/2 prime. So that's equal to 1/2 x to the minus 1/2, which means that f of f prime at c is equal to 1/2 of x to the minus 1/2. Nope, that's not x. That's our number c. My special value. And I'm going to set that equal to 1/4 because I found out that that's what it's supposed to be. So now I'm going to solve. And I think that what I want to do is I want to take that side to the -1, and I want to take that side to the -1. So I'm going to reciprocate both these sides because I want to deal with this negative power and these fractions. They're kind of annoying me. So the next line in my calculation would be that 2 times the square root of c is equal to 4. And let's divide by 2. And so we get root c equals root c equals 2. And so then c is 4. And we should double check our work. So here's a quick little double check. Is 1/2 of 4 to the -1/2 equal to 1/4? So let's examine that. So this is 1/2 of 1 over the square root of 4 equals 1 over 2 times 1 over 2 equals 1/4. Yes. Okay, so that was just a check of my work. And so I don't really need that anymore. So we found the c by taking the derivative and setting it equal to the slope that it was supposed to be and then solving for c. Okay, so here was solve for c, and I want to take f prime at c, and then solve for c equals special value. The mean value theorem says that no matter what the function, as long as it's differentiable on this interval, this process is going to work. Now, the algebra might be a real pain. Taking the derivative itself might be a real challenge. But the mean value theorem guarantees that you will actually be able to do that. Okay, so thank you very much for your time and attention today. I wish you happy average rate of changing. Bye.